Hello students, good evening. Welcome to Wallah. We are continuing our topics on theory of computation. Today is our lecture number 4. So in last 3 classes, we studied some of the important topics related to theory of computation regarding gate point of view. Today is our 4th lecture. The topic name for today's session is DFA, Deterministic Finite Automata. So in our last session also, we studied something related to deterministic finite automata, DFA. Today also, DFA is a very big topic, so that requires a minimum 3 to 4 lectures. So today is our last lecture on DFA. All right. Before going to that, just confirm me, audio and video is clear. Is it clear or not? Right. If you are having any problem with audio or video, just inform me so that we can rectify from here. Okay. So what are the topics we studied? So previously, the first topic we studied is if DFA is given, detection of language. This is one of the important one. DFA is given, detection of language. Right. The second one is DFA possible or not. For the given thing, DFA possible or not possible. Third one, yesterday we have studied expressive power concept. That one. Expressive power. So what is the expressive power of DFA? What is the expressive power of NFA? What is the expressive power of pushdown automata? Those things we studied. And then in the last class, just started construction of DFA. DFA construction. So in today's session also, the topic is on DFA construction. So these are the topics we covered till now. Before that, terminologies, what is language, what is alphabet, what is empty language, what is complete language, those type of things we studied. Then DFA definitions. This total things, mostly all these are comes under the concept of finite automata. All these are the concepts of finite automata. Right. So let us in today's session, let us focus on construction of the DFA. So you know the meaning of DFA already. If any new students are there in today's session, DFA is nothing but a finite automata. From every state, what is the property of the DFA? From every state, on every input symbol, one transition should exist. So if from every state, every symbol transition exists, that is only called as DFA. And that too, it is a 5-tuple one. Let me show you some of the DFA here. Observe this. I am showing 2 finite automata here. This is automata 1. This is automata 2. First one, is it DFA? Forget about this question. This is not, we'll come to this. Is it DFA? Here 2 states are there. From this state on 0 symbol transition exists. on symbol 1 transition exists. From state B on 0 transition exists, on 1 transition exists. This is clearly a DFA. Number of final states can be anything. Initial state is only one here. That's why no doubt clearly we can say it is DFA. 5 tuple definition satisfies for this. Come to the second one. Here 3 states are given, 2 final states are given. Is it DFA? Any number of states not a problem for us. Any number of finite number of states. From this 0, 1 transition exists. From this 0 transition, 1 transition. From the 0 transition, 1 transition. So perfectly there. This is also DFA. Now in today's session, for the given languages, we should be in a position to construct these type of DFA. That is what our today's concept. So we practiced all other possibilities regarding DFA. In today's session, we are going to study construction of the DFA for the given languages. Yesterday we studied one of the example. Today we will see different type of examples. What is the problem of, we will face some complexities in construction. There is a limitation for DFA construction. We will see what is the limitation, where DFA fails to construct for what type of languages. The topic already we studied yesterday, recollect that. So let me write one language here. This is the language. L equal to a power n, b power m, n greater than or equal to 1, m greater than or equal to 0. Now we need to construct DFA for this language. For yesterday, in yesterday's class, we constructed for one language. N, m both are 1. Is it possible, first of all, n value different, m value different, dependency is not there, n value independently we can select, m value independently we can select. So there is no problem to construct a DFA. We don't face any problem in DFA constructions. So now the question is how to construct. For that, first try to write the language. We have to write the language. Generate some minimum strings. If I take m value as 0, if the value of m is 0, how the strings are generated here? Only number of A's. 1A, 2A's, 3A's, and so on. Whenever you consider m value also, then A followed by B. 2A's followed by any number of B's. It can be anything. So these are the type of the strings possible in this language. The type of strings possible in this language is like this. Now we have to construct our DFA. What is the DFA? Deterministic automata accept all these type of strings. Now one more beautiful point here is DFA, deterministic finite automata, is having finite number of states. Hello everyone, good evening. Today our session is on DFA constructions. Yesterday just started in yesterday's class construction of DFA for one example only. Today we will see for different type of examples. Right. So we are constructing DFA for this in today's session. So start constructing DFA. From the initial state by taking one state as initial state here. Q0 is the initial state. How to construct this? No problem. If missed yesterday class, not a problem. You can understand today's class. If anybody absent for yesterday class, just watch that recording. That class is also important. But today also I am starting from basics. You can understand. All right. So to construct DFA, start from the initial state. accept the strings one by one, starting from minimum string. Accept A. To accept A, how our transition would be? Take one final state, starting from Q0 on A, reaching to the final state. On A, reaching to the final state. If you construct like this, A is accepted. Then we have to accept 2 A's, 3 A's, and so on. For this, we have to take one self loop. Then all number of A's will be accepted through these transitions. 1A, 2A, any number of A's will be accepted. Then A followed by B. A followed by B. How? A followed by B. For this, if we give transition, now AB string also accepted. After AB, one more B comes also, we have to accept here. For that, transition is like this. Now see this automata. Whatever the strings are there in first row, all strings will be accepted, and whatever the strings are there in A's followed by B's, any number of A's through this path, any number of B's through this path, all number of A's, all number of B's, whatever is there in this language, all the strings belongs to this language, definitely accepted by this automata. Right. Now the question is, is it DFA? What is our apply our definition of DFA? Now this automata accepting everything, whatever is present in the language, all those things accepted by this automata. But the question is, we are constructing DFA here. Is it DFA? Is it DFA? What is the definition of DFA? From every state on every symbol? No. From every state on every symbol, transition is required. Transition is not there, that is not DFA. Even though, see this automata, this finite automata, accepting all the strings of the language. Whatever is there in the language, all those strings accepted by this automata. But what is the problem here? The problem here is, after accepting everything, even though it is accepting everything, we cannot call as DFA because some transitions are missing. That's why whenever any automata is accepting everything, and just because of some missing transitions, if it is not become as DFA, then we need to add one beautiful state called as dead state. A dead state. Add dead state here. Whatever the missing transitions are there, see here, this state is clearly there. A transition, B transition. From this state on B transition not exist, add to dead state. From this on A transition not exist. So this is. So these states are called as dead states. What is the meaning of dead state here? Dead state is nothing but a non-final state. Dead state is a non-final state from which on every symbol transition exists. So once we fall into dead state, we cannot come back. That is the nature of the dead state. Now, how many number of states are there? 4 number of states. This is the DFA. No, right. Here in the construction of DFA, generally where students will get problem is, some of you are asking like this. Instead of this A, if I place B, what happens? If you place B, it will not become deterministic, right? Q1 on B multiple states. Understood? So that is the problem. If it is a B, Q1 on B multiple transition, it will not become DFA. a comma b on loop where here only, right? Very good. See, this is the problem of DFA construction. We will get different possibilities. You may think on different possibilities. Again, our friend asking, if I place a comma b, what happens without this state? Then what happens? See the language, every string should end with b only. The language in which every string should end with b. But if I write like this, a, b also will be accepted. A, then b, again a, then this. But the language clearly telling that after b, a is not at all allowed in the language nature is after b, a is not allowed. That is the nature of the language. That's why if I take it like this type of strings, wrong strings accepted. What is deterministic automata? Perfect automata, clear automata. What it has to give? For all valid strings, it has to tell accept. For all invalid strings, it has to say not accepted. This is the way. This is the problem. You may construct, you may think that this is the my answer is correct, but if at least one wrong string also accepted by your automata construction is gone. It goes wrong, we'll get negative marking. That's why the construction time. So better thing is, whatever the approach I'm explaining here, follow that approach. Start from the initial state, accept every minimum length string one by one, and proceed your transitions, states and transitions. Accept first A, give transitions according to this, 2 A's, transitions according to this, 3 A's, transitions according to this. Then remaining strings one by one, like that, complete all the strings. Then we will get the automata in a proper way. Right. One more thing, this language is finite language or infinite language? Clearly it is infinite language. Language is infinite. Automata is finite. Automata is finite because the nature is finite automata. That's why to accept infinite languages, definitely we'll keep self loops or loops somewhere. So where self loops, those things you have to identify clearly. Right. Is it clear for everyone? So this is the way. This is the way of construction. Like this, we will construct DFA for so many languages. Anyhow, in the examination, definitely they will ask how many states are there, how many minimum number of states are there. So we have to construct. What you have to practice is construction of DFA for the given languages very quickly. Practice is the only way. Take so many number of questions. Here also we will solve some questions. So this is a very basic one. We need to construct 16 states, 24 states, 12 states. By practice, we can construct in 2 or 3 minutes. It won't take more than that time. Right. Shall I move to the next question? We'll construct similar kind of DFA for one more language. Right. Construct DFA for the language. The language is looks similar, but construction time there is a lot of difference here. Some of you take some time, construct for this, and then can you give me answer how many states required for this? N value starting from 0, M value starting from 1. N value starting from 0, M value starting from 1. First, what is the first step here? Write the language. strings, generate strings. The minimum is, if I take n value as 0, 1b, 2b, 3b, and a is followed by b's. How many states generally you are getting? Just tell me number of states, that is sufficient. And I am constructing, you can verify with your answers. Right. So what is the first string? Go from the minimum strings onwards. It is not same as previous one. There is a small difference here. It's not visible. Okay. I don't use. First B, accept B. Starting from initial, accept B. Go like this. If you construct, it is easy. Take the minimum length string, accept, then double B. What is the double B? 2 B's, 3 B's, infinite B's, or any infinite things are going on, compulsory loops required. Loops are cycles because it is a finite nature, language is infinite nature. So all these B's, number of B's accepted, any number of B's accepted with this. 1B, 2B, 3, any number of B accepted. Then AB, A followed by B. How to accept this? A, B to accept this, start from the initial state. B transition is there for A here only. So what happens? A, B accepted. Then A double B, A double B accepted. 3 A's, 1B. So any number of A's, A value can be anything, B value can be anything. These type of strings, any number of A's through this loop, any number of B's through this loop accepted. This automata is accepting all strings belongs to this language. It's very easy. This automata is accepting all strings belongs to this language. Am I right? Now the question is it DFA? DFA means any missing transitions, those things we have to check. Is it DFA? Any missing transitions here? Yes, there are missing transitions. So from here AB is there, from the last state we don't have, so we have to add a state. Name of the state is dead state. Dead state is a non-final state. From this on A, on B transition exists. So from this on A, it is going to the dead state. So dead state is a non-final state. Now 3 states. So total number of states required. The previous example, that is different. Language seems to be almost same. That's why I'm saying language to language way of construction completely changes. So here no copy paste operations will not work here. If you apply copy paste, if you by heart, those things will not work. So logical things, problem to problem, you have to design by your own. That's why we are getting many questions from this topic. All the topics of theory of computation like this only. How to think, there is a logic, there is a trick, based on that you have to solve. Right. Any confusions in this? Any confusions? Yes, 𝐂𝐚𝐿. I'm teaching whole subject, not in a complete I'm not teaching all concepts, almost all concepts. Here I am not solving all complete gate questions, those things not involved. So most of the topics I am covering here, majority. Right. Yes, it is a fast track one. So I'm going to complete most of the topics quickly. Right. So anybody facing any difficulty in these constructions? Still any difficulty? Can we move to some other? Now I'll give similar one, looks like almost same, but here also number of states may differs. The problem is completely different. So let us try for this. This is what we have to practice. So similar questions, different answers. The gate paper also options are like that only. Nearer options. The options are almost nearer to our correct answer. Yes, trap definitely there. That is gate paper. So they will try to trap you. Those who are confidently solving the question, getting answers without falling into trap, they are toppers. So my intention is, while giving these type of questions, you have to come out of the trap. A power n, b power m, n m value greater than or equal to 0. N value, m value both greater than or equal to 0. So in the previous one is 0, one is 1 like this, but here both starts from 0. How many states? Here also for this question also many students generally do mistake. Majority of the students constructs this way. Most of the students constructs this way, but is it correct? According to me, this is not the right answer. If it is that much, that is not the right way. So first identify language, strings of the language. If anybody constructed of this nature, that is clearly wrong. Identify strings. What is the minimum string? The minimum string clearly epsilon. A value 0, b value 0, both are 0, epsilon. Whenever m value 0, only A accepted. Only B accepted. A is followed by B is accepted. So these are the type of the strings. What is the problem if I construct like this is, it will accept string BA also. The string BA not belongs to the language. String B is not present in the language. If it is not present in the language, how can we construct like this? Any answers? Anybody constructed? Any answers? Right. I'm constructing for this. First, to start from the initial state. Accept minimum string. What is the minimum string here? The minimum string here is epsilon. So to accept epsilon, initial should be final. Initial is final. Then if you want to accept any minimal string, initial should be final. Then all number of A's, to accept all number of A's, loop on A. Then to accept B, don't give like this. I told you wrong strings accepted. If I take the B loop here only, wrong string B also accepting. That's why on B, so many number of A's we have to accept, but not by using this final state. It is accepting wrong string. That's why take one more final state. On this, make a loop. Now look at this automata. Now it is accepting epsilon, accepting only number of A's, accepting only number of B's, A's followed by B's. Any number of A's followed by any number of B's. This is the nature of the strings accepted by this. So all strings accepted or not? Epsilon accepted, all A's accepted, all B's accepted, A's followed by B's also accepted. Any number of A's followed by any number of B's. Now this is our automata. This is our finite automata, accepting all our possibilities, all our possible strings. So whatever is there in this language, all these things accepted by this automata. After accepting all this, can I call it as DFA? Is it a valid DFA here? Still no, because missing transitions are there. What is the missing transition? Q1 on A, there is no transition. That's why add a state called as dead state. So from here on A, now this is our perfect DFA. 3 states. This DFA, previous one, both are, even though states are same, both are different things here. So number of states, even though same, they are different. So like this. So A power n, B power m, n, m values whenever 0, the DFA looks this way. N value 0, m value 1, DFA looks like this. Here only one final state. For this, 2 final states. Transitions also different. From language to language, it varies. Always same DFA, no guarantee of getting. This DFA, n value 1, m value 0. They are almost similar, but whenever I am changing the values, n and m values, we are getting different varieties of DFA. Right? So how many states? So for this, 3 states. This is the basic, some of the basic way of construction of DFA. Can I give one more? Can we construct for DFA for one more? a power 2n, n value greater than or equal to 1. How many states required if you construct DFA for this? How many states required if we construct DFA for this? Same thing, first generate the strings nature, how the strings will be generated, find out. This is also infinite language. Infinite language. We have to construct finite automata for this. Whenever you are constructing finite automata for infinite languages, definitely self loop or cycles we have to take. So here for this, whenever you are constructing DFA, cycle exists. Yes, cycle exists. So by using the cycle, total number of infinite strings we can accept. Very good, 3 states. So start constructing DFA for the minimum string first. What is the minimum string here? 2A's. To accept 2A's, we are going to final state. Then 3A's not there, 4 accepting. 4A's not there, 5 accepting. Oh, sorry, 4A's accepting, 5 not there, 6 accepting, 7 not there, 8 accepting. Like this, some students are having doubt, how many symbols present in the language? You tell me how many symbols present in this language? Is there any symbol B here? So previous A, B's are there. Here any symbol B? So don't go to dead states. The language is formed over only one symbol. Our sigma is nothing but only A. So there is no confusion on symbols. Right. Then whenever it is, if any common difference present between strings, this is going on, keep on infinite times, then to accept that common difference, we can maintain cycle, 2 length cycle. Now see this automata, accepting 2A's, 3 rejecting, 4 accepting, 5 rejecting, 6 accepting, like this. So to accept this infinite nature, sometimes if common difference 1 going on, then we'll take self loops. If there is other common difference, by using like these cycles, we can handle. Some students may answer like this also. They will take this as the final state, Q0 as the final. What is the problem? They will take self loop like this. If you take Q0 as final, because some people may get this type of doubt also. If Q0 is final, epsilon accepted, 0 length string accepted, but the n value starting from 1. That's why the number of states is 3 states for this automata. Yeah, if other symbol B is there, then so many B transitions are missing. Here from this state, only one symbol is there, A transition exists, from this A transition exists, from this also A transition exists. Every state symbol transition exists. This is clearly DFA. It's clearly DFA. That's what, n value greater than or equal to 0, then situation is different. N value greater than or equal to 2, then situation is different. Depends on the minimum string, depends on this condition, the automata states changes, final states changes. Here according to this situation, this is some other, then we have to construct separately. Right. We'll go for one more. Construct DFA for the language, almost similar one. A power n square, n greater than or equal to 1. Previous one is 2n, 2 times of n. This is square of n, n square. How many states when we are constructing DFA for this? So how many states, Gokul? Previous states. Okay. Number of states, how many? Write language, construct automata, the task is yours. Total task is your responsibility. I am expecting number of states from you. How the strings? If n value is 1, n value is 2, n value is 3, n value is 4, 16, and so on. I am expecting number of states. Gokul saying n states. See, automata state should always be finite. Tell me some finite number. 3 states, 4 states, 5 states. 5 states. Okay. Forget about number of final states. You can take, according to the strings, you can take any number of final states. In gate papers, they generally ask about number of states, total number of states. They don't ask number of final states. We don't bother about final states, number of states. Okay. Okay, okay. 𝐂𝐤𝐬𝐬. Okay, madam. Right. Now, I'll give answer for this. Wait for some time. I want to give one more question. Please try to construct DFA for this. Find out. Many people are feeling difficulty to construct for previous one. At least construct for this. A power 2 power n, n value greater than or equal to 1. How many states for this? 2 power n. For the previous one, I'll construct. By that time, just people, you people can try for this. A power 2 power n. Write the strings first. n value starting from 1. Strings nature is like this. For these strings, if we construct, right. So if we construct DFA for this, how many states? Two states. Okay. Remaining people, you can try. The answer I am constructing for the previous one. Answer for the previous one is this is the answer for the previous one. 5 states, 4 states people. Verify your answer once. DFA not possible for the previous one. For this one, DFA not possible. Traps, theory of computation, subject means trap. There are so many topics of this type. Right. So DFA not possible. For the previous one, not possible. Don't try to construct. Even if you try for 100 years also, DFA not possible. You cannot construct. It is not possible to construct. For this as well, it is not possible to construct. I am not saying difficult. See, there are two terminologies in theory of computation. We have to use them carefully. Difficult, not possible. So difficult is even after trying for 1 week or 10 days, you may construct. But here, not at all possible. Try for 1000 years also, it is not possible. Because see the previous one. For this we can construct. We constructed already. How to know? That's what I am explaining. See, whenever you are generating strings from symbols, if there is a common difference, 2 is a common difference. Common difference between strings exist for such type of infinite languages. If the first thing is, if the language should be infinite. For finite languages, we never get a problem. For every finite language, we can construct DFA. Whenever the language is infinite, then if common difference present between strings, those infinite nature we can handle by using self loop or cycle. But whenever common difference is not there, see here, do you have any common difference? What is the difference here? 3. What is the difference here? 5. What is the difference here? 7. Where is the common? There is no common difference. Common difference not exist. DFA not possible. Understood this point? So here also same. Like this, whenever language formed over one symbol, generate the strings. Is there any common difference between the strings or not? Verify. So many times we got question in GATE paper based on this for 2 marks. There are some questions for 2 marks also. The coming classes also similar kind of things we'll study, but anyhow, the reason for this type of language not becomes regular. This language is called as non-regular languages. Why they are non-regular means DFA is not possible. The reason for DFA not possible is common difference not exist. Here, do you have any common difference? 2 is the difference here, 4 is the difference here, 8 is the difference here. Where is common? There is no common difference. If common difference not exist, DFA not possible. Understood? So this is the way. So in the construction time, DFA construction time, just a keep on construction is not sufficient. So there are some trap kind of things. That's why we need to identify whenever we are constructing DFA for the languages, is it possible or not? So in previous classes we have seen comparison. In our yesterday class we studied comparison. So the reasons, somebody asking why means it is finite automata. Infinite things if you want to handle by finite, infinite things if I want to handle by finite, repetition required. Repetition means loops or self loop. Yes, the common difference is called as arithmetic progression. Anyhow, the terminology is whatever it may be, I am using it in a simple terminology. So that is a reason DFA not possible. If anybody want more reasons for this, wait until pumping lemma. There is a concept called as pumping lemma. By using that also we will prove. Okay, right. Is it clear? Okay, then I will move to one more concept. Is it first one DFA? Tell me. First one DFA. First one is the DFA. Very clear. Both are DFA. Both are DFA. Then whether both are accepting same language or not. They are accepting. Here 2 states are there, 3 states are there. Because if I minimize this, we may get this, may not get this. So they are accepting same language or not. Sometimes, what is the language accepted by this DFA? The question we may get like this: which of the following DFA accepts same language as the given DFA? The questions are like this. We have to equate the language accepted by given DFA are equal or not. From language point of view, that is very difficult because the languages are infinite. Loops are there, infinite languages. Infinite comparison is impossible. That's why from DFA it is very easy. So let us see. We need to perform a comparison. So in order to check language accepted by this DFA, language accepted by this DFA, same or not, start from initial states of both automata. Initial state of this is A, initial state of this is C. Start from initials of both. Take the transition. 0 transition. A on 0, where it is going? A. C on 0, where it is going? D. Similarly 1. A on 1, where it is going? B. C on 1, E. Right. So start from initials of both, take their transitions. On 0 transition, on 1 transition. Here we have to compare one thing. In the coming result, if both are finals, then okay. Both are non-finals, then okay. If both are finals, we can say they are equal. Both are non-finals, we can say they are equal. If you are getting any final non-final combination, immediately stop there. We can conclude not equal. Let me repeat this point. So start from initials, take 0 transition. On 0, coming result in which both are final states, then they are equal. Both are non-final states, then also equal. If you find any final non-final combination, that is not equal. So here till this case equal or not equal, tell me. Any final non-final combination here in every pair? So both are finals here, A and D. A is final, D is final, it's okay. Then B is non-final, E is non-final, non-final also okay. So then we have to continue this process. For every new pair you perform the same concept. For every new pair perform comparison, that is AD. AD. A on 0 A, D on 0, D on 0 D. See the transition, A on 0 A, D on 0 D. So AD on 0, final no problem. E on 1 B, D on 1 E. Non-final no problem. So like this, for every newly coming pair we have to perform this comparison. What is the next one here? BE. Still completion of all new pairs we have to do this process. So B on 0 A, E on 0 C, B on 1 B, E on 1 E. So this is A, C, final, B, non-final. Now also okay. Any new one? Starting procedure is very easy to check both are equal or not equal. Starting from initial, 0 transition, both are finals okay. 1 transition, both are non-finals okay. New pair I have taken, started comparison. AD on 0, AD, both are finals okay. On 1 BE, both are non-finals okay. Then new one BE. For BE on 0 transition A and C, final okay. On 1 non-final okay. Is there any new pair here? Still AD already over, BE already over, AC already over. All possibilities completed. Till the completion of this, we never find any final non-final combination. So we can conclude that the language accepted by these two automata is similar. So language accepted by this, same. Why? Because even though it is having 3 states, we can reduce this to this. So this is the way. Is it clear, this one? I want to give you one homework kind of thing, small task. So I am giving 2 automata here, both are DFA. You need to find whether language accepted by these 2 automata same or not. The initial of this is A, initial of this is E. This is the task. Right? It's easy. So automata seems to be very bigger, and we are comparing, keep in mind, we are comparing infinite languages in a small amount of time. So self loops are there. Language accepted by this automata infinite. Language accepted by this automata also infinite. Now the question is, are they accepting same language or different language? So in order to find, still if anybody having doubt, I have explained that procedure already. Watch that recording. So start from both, initials of both, start from here. Take A transition, B transition. On A transition, both are finals, happy. Both are non-finals, happy. If you are getting any final non-final combination, stop there, conclude they are not equal. At least one time also final non-final sufficient, stop there, and you can say that is non-final, that is not equal. So all of you try for this question. So tomorrow some people are asking about tomorrow. Tomorrow mostly we are focusing on NFA or any other concepts like minimization, those things. Minimization of DFA and then NFA. These are the topics. This is just a practice question, not asked question in GATE. Right. Okay, students. That's all for today's session. If anybody want to write this question, I'll display the same one. Thank you also with this slide only. Thank you for everyone. If you want to note down this question. Anyhow, it is there. After this, pause the video, note down these transitions. Okay. We'll continue tomorrow at the same time. Once again, thank you all. See you in next session. Good night to all of you.